So this is where we left in the last class. So now the question is, we understand what forces are, right? But is that sufficient? It is not sufficient, because if you want to rotate something, you need more than forces, right? So you guys probably entered the classroom when you came in. Did anybody try to push on the hinges to get in if the door was closed? Have you ever tried that? Maybe when you were a kid, right, you were curious, why can't I push on the hinges and open the door? You can't, right? So clearly you could apply as much force as you wanted on the hinges, but there is no way you'll be able to open the door, right? If you are trying to use a screwdriver to, let's say, tighten or loosen a nut or a bolt or a screw, you know that if your force that you're applying on the nut is far away from the axis of rotation, you have a much easier time opening or tightening something, right? You know, you guys, most of you probably drive a car or have some experience at least sitting in the car and trying to drive it. I have a 2.5-year-old son. He tries to do that all the time because he likes to drive cars. So he sits with me in my garage and, you know, he just tries to do. Anyway, so you guys drive a car, right? Now, if somebody said, you know what, I'm going to give you a steering wheel, but that steering wheel is going to be really this small. What would you say? Well, now you'll be probably muttering unspeakable under your breath, right? So it's not going to work. So clearly, it's not the forces alone that will make something rotate. If you want to rotate something, you need more than forces. And what is that quantity? So we have a physical quantity for that, which we call moment or the torque. Okay? So torque is usually a word we reserve for the moment that the shaft of an engine or a motor applies on a load. So we won't really use the word torque when we're talking about the moment. The moment we start talking about the DC motors and engines later on in the semester, we will say, hey, this is the torque that this motor can apply. Okay? But moment and torque basically are otherwise same things. Okay? It's just different contexts where we use those two words. So how do we capture this notion that you need the force and you also need a little bit of distance from the axis of rotation or the pivot point, right, about which you want to rotate something? The definition of the moment is really very simple. Okay? This is the simplified definition, which says that the moment is defined by the force, the magnitude of the force that you're applying, times the perpendicular distance from the line of action to the point of interest. Okay, let's see what that means. So first of all, magnitude of the force, we understand that, right? How much push or pull you're applying. What is the perpendicular distance from the line of action to the point of interest? Line of action is basically nothing but the direction a force acts. So in this case, if you apply this force F in this direction, that line along which this force is acting is called line of action, because force is like an action. Okay? Then D is the perpendicular distance from the point of interest, which is most of the time is the pivot point or axis of rotation, to this line of action. So if this is a pivot point, because you're trying to rotate this nut, then perpendicular distance would be the distance from this point, and you draw a line that will be perpendicular to this line of action, and that's this line, right? So that would be the D. Okay, so that's the definition of the moment. Now, later on you will see that you will have a much more rigorous definition for the moment. In this class, we are mostly dealing with the forces and the moments, everything in a plane, right? When you get into the three-dimensional objects where you try to compute the moment, you will be better off using a proper definition that involves cross product of a position vector with a force. So if anybody is in the statics class, you probably learned the definition of moment as R cross F, right? And this definition is a simplified version of R cross F. Okay? So because in a plane, we really don't need to worry about the cross product. We can just multiply the perpendicular distance with the force, and we can figure out which direction the moment is going to be acting. And I'll show you that in the next slide, how to figure out the direction part. All right? So that's the basic definition. Force times perpendicular distance, right? And sometimes that perpendicular distance is also called the lever arm distance. Okay? So longer lever arm you have, more moment you can apply with the same force. Okay? All right, so let's look at a few examples. So in this case, we have a hand that's trying to maybe screw this nut or going to unscrew this nut, right? So we want to compute the moment due to this force, right? So what is the moment? Moment would be this force magnitude, whatever it is, right? So how do we write that? We put the bars around the force vector, and that tells you that's a scalar quantity, times the perpendicular distance. So do a little bit of trigonometry. If this length, the distance from here to here is L, and if this angle is theta, right, then this is a right angle triangle, so this would be L cosine theta, right? So the moment is L cosine theta times the magnitude of F, okay? All right, that's good. So we can compute the moment due to this force. Now, another way to compute the moment is by using the component method. And both of these methods are discussed in your textbook. So first method that I just spoke about is called perpendicular distance method. The second method is component method. So what is component method? Really very simple idea. We already know that if we have a force in a plane, we can resolve it along component direction, Cartesian axis directions, right? We can always break it down into two components. So if we pick a coordinate system, right, and in that coordinate system we resolve this force along two perpendicular directions, then I can also write the moment of this force by computing the moment of the two component forces, right? So how can I resolve this force F? Well, let's say this is my, one axis, okay, and this is my other axis, right? So this is perpendicular to this line, essentially, and I've just picked that, okay? So if this angle is theta, then this component would be F cosine theta, and this component would be F sine theta. So now instead of trying to compute the moment of this force by looking at the perpendicular distance, I can look at the moment of these two quantities alone and then add them up. Okay? So what is the moment of F cosine theta? Well, the moment of F cosine theta would be F cosine theta times the perpendicular distance. Now in this case, finding the perpendicular distance is really very easy because I know this length is L, right? So the moment of F double prime, which is what we're calling F cosine theta, is F cosine theta times L, right? Okay, so that's the moment of this component of the force. What about the moment of this force? Okay, so this one is pointing that way, and that's F prime, F sine theta. And what is the perpendicular distance between this force, line of action, and the center point of nut? 0. Why? Because this line of action is actually going through this point, right? So there is no distance between the two, which means that the moment of this force is actually equal to 0. And that kind of, matches with your day-to-day experience, right? If you were trying to open this nut and you had this wrench in your hand, if you pulled on the nut, there's no way you'll be able to rotate it. And this one is a pulling force, right? So there's no moment due to that force. So if you add the moment of these two, basically there is no contribution from this, but there is contribution from this one, and that is nothing but F cosine theta times L. And now you see, this one is same as this. So it doesn't matter which method you use, you will always get the same answer. So you can use either the perpendicular distance method or you can use the component method. Okay? But you can't do both of them, right? Because then you'll be double counting for the same force, right? So once you resolve a force along component direction, you can compute the moment of both of them, right? So in this case, we really didn't have to worry about how to add the two moments because one of them was 0, right? So let's talk about direction. So if you could in general have some moment that will be positive, some moment that will be negative. So the question is, how do we find out which moments are positive, which moments are negative, right? Okay, that's very, very simple actually.